Hello and welcome to the third live session of the course Advanced Dynamics. I am Anirvan Dasgupta from the Department of Mechanical Engineering at IIT Kharagpur. This course had started on 24th of July, and we are into the 11th week approximately. Next week is the final week, and we have covered quite a bit of topics since our last live session. Let me briefly go through these topics, and in the meantime, if you have any query or question or any doubt or any feedback that you would like to give, you can type on the chat box, or you can use the Google spreadsheet which was shared with you. You can also write to us on the forum, but that will be taken up separately later. Okay, let me just discuss a few topics. If you have any query, please keep writing to me. In the last live session which we had, which was in about the 7th week, we were discussing, we had just started with the spatial kinetics of rigid bodies. We had discussed about the spatial kinematics, and here you might have seen that the kinematics in spatial, in 3D, spatial kinematics, brings in a little more advanced. I mean, you have to be a little more careful with derivatives. But our prescription for taking time derivatives remains the same. Only thing, you'll have to be careful in applying it. Recall that the total time derivative of any vector quantity is given as the local time derivative, which we used to write as del t, plus omega frame cross. And here we started off with finding out angular acceleration for a prototype body, which was like an axisymmetric body spinning with a point fixed. You can take the example of a top, if you like. And there we had seen that we can have different kinds of motion. For example, you have definitely the spin of the body about its axis of symmetry. And then we had two further motions, nutation and precession. And even when it has a constant spin, if it has nutation and precession, then you have acceleration. And this we formalized by writing out the net angular velocity of the body as the angular velocity of the frame in which we are representing things, and velocity of the body with respect to the frame. In case of axisymmetric body, it is very easy to fix up a frame by taking the z-axis as the axis of symmetry. And we had taken the origin of the frame at the point at which it is in contact with the ground. So with that frame, we had discussed and this frame was set up also in a special way. We had taken one vertical z-axis, which is fixed, and the z-axis of symmetry of the body, which might be tilting. And we took the cross product of the fixed z and this axis of symmetry of the body, and we defined x-axis. And y-axis was completed as a right-hand coordinate system. Now, with this frame set, we defined nutation as the rotation about the frame x-axis, and precession as the rotation of the frame about the fixed z-axis, the inertial z-axis. And we determined the rate of change of angular velocity, which gave us the angular acceleration. So that was found as the local derivative of the angular velocity plus the frame derivative. So in the frame derivative terms, recall that we had the angular velocity of the frame, which consisted of the nutation and the precessional angular velocities. Okay, so that was the kinematics, which was a little special, a little different from what we had been doing previous to that. Then we moved on to the spatial kinetics of rigid bodies. Now in spatial kinetics, we have two equations essentially. One is the extension of Newton's second law for rigid bodies, which tells us that the rate of change of linear momentum of the center of mass of the body is equal to the sum of all forces acting on the body. This was one equation, the translational dynamics equation, and we had the rotational dynamics equation, which was written in terms of the angular momentum written about the center of mass, and the rate of change of angular momentum about the center of mass is equal to the moment of all forces about the center of mass. This was used, and once again, because we were expressing the angular momentum of the rigid body in terms of the moment of inertia tensor times the angular velocity. Here we had to be a little careful because this moment of inertia tensor is a 3x3 matrix, symmetric matrix, of course. And if we have an arbitrary frame in which we are representing the angular momentum, in that case, the moment of inertia tensor becomes time dependent. So it is much better to fix the frame to the body, which we did. And in that case, the angular momentum about the center of mass is equal to the moment of inertia tensor Ig, which means the moment of inertia tensor about the center of mass times the angular velocity of the body. So this Ig is a constant matrix. Now, when we come to the rotational dynamics equation, we have to time derivate this angular momentum vector. And because Ig is fixed by virtue of fixing the frame to the body, we had the differential equation which had Ig omega dot, where omega dot is the local time derivative of the angular velocity, plus omega of the frame cross Ig omega. So this second term came from our previous discussions. So the local derivative and the frame derivative. And so in total, what we had in the rotational dynamics equation was Ig omega dot plus omega of the frame cross Ig omega equal to the net moment about G. So that was the rotational dynamics equation. If for a general fixed frame to a body, we have 6 independent entries in the moment of inertia tensor. But if I can choose a very special frame known as the principal frame, then the moment of inertia tensor becomes completely diagonal. In that case, we have only the 3 diagonal elements of Ig, and all the other off-diagonal terms become 0. That makes the equation very simple, and that's called the Euler's equation of motion. So that's the rotational dynamics equation. So that we discussed in the 7th week. Then we moved on to we looked at examples involving spatial dynamics of rigid bodies, where a number of examples were solved. And then in the 8th week, we came to this very interesting topic of gyroscopic motion. Whenever you have a body which is, we took this example of axisymmetric bodies. Whenever you have a spinning body, and if you apply a torque to this spinning body, which is this torque not being along the direction of spin, maybe perpendicular to the direction of spin, then a very strange behavior is observed, which is known as gyroscopic motion. If you have played with tops, then you know that you have seen that initially the top seems to be spinning absolutely upright. But as the speed comes down because of dissipation, you start seeing wobbling of the top. We have precession. We also have nutation of tops, which will be in discussion later in this course. Okay, so so this gyroscopic motion occurs when you have a spinning body which is being acted upon by a torque, maybe perpendicular to the direction of spin, making an arbitrary angle, non-zero angle with the direction of spin. Then the kind of motion that occurs is known as gyroscopic motion. You have precession and nutation. Using these ideas, we have discussed some examples of boomerang, for example. For one, we have shown how the rotation of the motion of the boomerang can be explained by considering the moment produced by the aerodynamic forces. As you know, a boomerang is a device which, when given a spin and a throw, comes back to the thrower if it doesn't hit something. And this is used by the aborigines of Australia and elsewhere. So this has very interesting dynamics, as we have discussed. The aerodynamic forces, it's designed in such a way that the aerodynamic forces provide a moment which is perpendicular to the axis of spin, and that creates a precessional motion. So the axis of spin rotates, and if the axis of spin rotates, then its motion also changes direction. The translational motion also changes direction. So that was one example that we had looked into. And why do we have moment? Remember that we are throwing the boomerang, and the blades which are at the top, their velocity is slightly higher than the blades which are at the bottom. So that change in the difference in these velocities create different lifts in the two blades, and that causes a moment, and that gives a change in direction of the motion of the boomerang. Next, we discussed about precession of the Earth, the precession of equinoxes. This happens because of moment, because the Earth is actually not a perfect sphere. It's an oblate sphere. It's an oblate-shaped body, and because of that, and the presence of the sun, which is the source of gravitation for keeping the Earth in orbit, Now, if it's oblate, because the Earth is oblate, it creates a torque. The reason being the axis of the Earth is inclined at around 23.5 or 23.4 degrees. So you can imagine that this one lobe of that, one part of that oblate thing is closer to the sun, the other is slightly farther from the sun. So the change, that the difference in the attraction causes a moment. And this moment, and because Earth is spinning about its axis, the north-south axis, this moment creates a precession. So it's called the precession of equinox. With respect to distant fixed stars, the direction of the north-south axis of the Earth is changing. Had Earth been a perfect sphere, or the axis had not been tilted, in that case, the axis would have pointed in the same direction. So even if the Earth were a sphere, perfect sphere, then this inclination of the axis would not have changed direction. It would have remained inclined and pointed to the Polaris. Right now, it is pointing to the Polaris, the north, the pole star. But because of this precession, after about 16,000 years, this axis is not going to point towards the Polaris. Remember or realize that this Polaris, the distant stars are roughly fixed stars. So if it is not pointing to the Polaris, which means the axis has reoriented itself. And the only way to explain this is the gyroscopic motion of the Earth. It's called the precession of equinox. What happens because of this? With respect to the distant stars, which sets up our inertial coordinate system, the portion of the orbit where you have the equinoxes, that keeps rotating. It keeps rotating. So the location at which on the orbit of the Earth around the sun, the location where you have spring around this time will change, will go to that point where we have autumn now. So maybe after 16,000 years approximately, the location on the orbit where we have spring will have autumn, and where we have autumn now will have spring. So this is called the precession of equinoxes. So this is another very interesting phenomena, natural phenomena that happens. Then we also looked at the Chandler's wobble, which is a torque-free precession of the Earth. This happens once again because this Earth is an approximately an axisymmetric body, which is spinning about its axis. And we have discussed this in kinetics, that we have torque-free precession, like you have torque-free precessions of the frisbee, right? We have torque-free precession of the frisbee, so they wobble even when you do not have torques. You have torque-free precession of rockets and other spinning bodies in space. In a similar manner, the Earth also precesses this. So this torque-free precession is called Chandler's wobble. This has, of course, I mean, Chandler's wobble has been missed for quite some time because the precessional angle is very, very small. The axis of precession, it deviates very little from the north-south axis. But it was eventually resolved, and it has been determined. So we had discussed about Chandler's wobble. Then in the 9th week, we started off with the rotation matrix, kinematics of rotation. We have looked at representation of rotation matrix, their interpretation, how to compose multiple rotations, and how to parameterize rotations. For example, we have used Euler angles to represent or to parameterize rotation. We have used roll pitch yaw. Then we have also used the Euler axis angle. You see, any rotation can be represented by a single rotation about an axis. Using this is called the Euler axis angle representation. And we have also used the quaternion representation for rotation, for representing rotation, unit quaternions. And that was derived, or that was, this representation fell out from the Euler axis angle representation. So all these things were discussed in the 9th week. In the 10th week, we started off with analytical dynamics, Lagrange's equation of motion, starting from the Hamilton's principle. And we looked at a new way of deriving equations of motion based on energy principles. We defined a Lagrangian, which for mechanical systems is the kinetic energy minus the potential energy, and we have seen the Euler-Lagrange equation of motion. If we can write down the kinetic energy and potential energy, you can construct the Lagrangian and derive the equation of motion. This approach is in many ways simple, because here you do not have to worry about internal forces. In Newtonian dynamics, you have to draw free body diagrams, you have to write down the equations and eliminate the internal forces to finally get to the equations of motion of the system. In the Lagrangian approach, and it's also called the analytical dynamics approach, you don't have to do all these things. You don't have to worry about internal forces. You have to just write the kinetic energy, potential energy. Of course, you have to carefully do the kinematics. And once you have the Lagrangian, it's absolutely algorithmic how you derive the equation of motion. So we have seen how to derive equation of motion for various systems under various conditions. Like in the 11th week, which we are currently in, you must be going through the discussion on system with constraints. How in presence of say holonomic constraints, so scleronomic constraints, how we can still write down the Lagrange's equation of motion. This we have discussed. By the way, we have also discussed Lagrange's equation in the presence of non-conservative forces for which you cannot write potential energy. So that was called the Hamilton-Ostrogradski principle. And with that, we had derived equations of motion with for systems with dissipation or external forces for which you cannot write potential energy, so non-potential forces. So this week we are discussing systems with constraints, and in the next week we will be looking at symmetries and conservation laws, how the symmetry of the Lagrangian leads us to a conserved quantity. By symmetry, what we mean is, for example, under a transformation, when you have the coordinates, you have the generalized coordinates with which to write down the Lagrangian. So if you transform the coordinates, go to a new set of coordinates, and under this transformation, if the Lagrangian does not change its structure, then you have a conserved quantity. So this is called a Noether's theorem, and this we are going to look at next week. So this is more or less what we have covered or what we will be covering in this course. I hope you are able to you are doing the assignments, you are able to do the assignments. If you have any difficulty, please write to us on the forum. You can write to me right now if you have any question, or else you can always get back on the forum, and we'll try to help. We have the TAs who will be helping you, and if you have any feedback to give, please give us on the forum. Just before ending, let me summarize or tell you a little bit about the exam, which is on 29th of October. The exam paper will have about 20% of multiple choice questions from the lectures. So 20% MCQ questions from the lectures. These are called the recall type questions. You have to recall what was discussed in the lecture, and based on that, you have questions directly from the lectures. 30% of the MCQs will be from the assignments. So please do the assignments seriously. Please complete those assignments and submit. And the rest will be new questions. So 50% from the existing material, the lectures and the assignments, and 50% from will be new questions, of which 20% will be MCQ and about 30% will be numerical answer type. So that will be the structure of the question paper. If you have any query or if you have any feedback, please give us in the forum. I think we will stop now. So I would like to thank all the TAs in the course. I would like to thank you as a participant. And I would also like to thank the NPTEL staff for making this live session possible. So thank you, everybody. We'll sign off here.